Hello everyone. So this module
So
basically focuses on examples of multimodal simulations for the STEM. So this module basically focuses on teaching and learning best practice for using multimodal content in STEM education, and we will elaborate some examples of multimodal simulations for the STEM education. So multimodal auditory, visual, and tactile e-learning framework. The metaverse, a shared virtual space where users can interact with each other and digital objects in a more immersive and realistic way, has the potential to revolutionize e-learning. By integrating educational content into the metaverse, students can engage in a more interactive and personalized learning experience, providing a more engaging and realistic experience. So, with the use of virtual reality, augmented reality technology, and haptic devices, students can engage in hands, laboratory work, and practical experiences in a safe and immersive environment. This technology could enable students to interact with each other and digital objects in a real time, collaborate on projects, and receive feedback from instructors. Moreover, the metaverse could offer a new platform for educators to deliver their content, enabling them to create interactive and immersive educational environments that could enhance learning outcomes. This technology could also offer students from different parts of the world to access to high quality education regardless of their location or socioeconomic background. Overall, as we have seen, the potential of the metaverse for e-learning is vast, providing an opportunity for educational institutions to, to transform the way education is delivered and assessed. So, the senses usually employed in multi-sensory learning are visual, auditory, kinesthetic, and tactile. So we call it VET. Seeing, hearing, doing, and touching. The recent advancements in virtual reality and augmented reality and haptic technology may potentially enable the possibility of extending the multi-sensory learning approach to e-learning and for redesigning study modules and engineering remote laboratories. Through this strategy, the community of educators and students may be enabled to explore the new frontiers of the education. Starting from complex and cumbersome desktop haptic interfaces, in the last few years, many research groups have proposed wearable haptic interfaces which enable a multi contact interaction with virtual or remote objects. This opens up the opportunity of a new generation of e learning contents that includes tactile experience. The main roadblock toward the spreading of this technology is the current cost or complexity of the proposed solution that must also include a reliable hand tracking system to achieve a possibly large spread of solutions allowing the developments of tactile contents. It is necessary to develop systems with a reduced cost by using commercially available off the shelf components. So, as we can see, to achieve such a goal, our team proposed a framework architecture encompassing software, hardware, and multimodal rendering strategies. The primary components of the proposed framework are the components of the shelf, valve, knuckles, EV3 controllers. These controllers combine complex sensor input to track hand position, finger position, motion, and pressure to determine user intent. We have equipped these controllers with precise shaftless vibrotactile motors embedded on the outer shell. Distinctive haptic feedback patterns may be communicated to the user via these motors, accurately simulating virtual finger collisions. The controller for the motors is implemented on an Arduino Mega board. The Arduino is an open source electronics prototyping platform that uses flexible, user friendly hardware and software. The Valve Knuckles EV3 controllers, which are augmented with vibro-tactile motors, represent a significant advance when compared to similar devices since they are easy to obtain by just having simple additional components and they are resilient and low cost. The Steam VR application programming interface is used for the integration with the visualization environment. The Unity cross-platform 3D environment is chosen as a middleware for the integration of all framework components. The HTC Vive Pro VR headset is adopted to provide the user with realistic visual feedback. A common computer monitor can also be used to lower the cost, and with the bi-directional audio channel to enhance the user experience. So the this slide is basically describing the control circuit for one vibrotactile actuator, which is basically shown here. The motors are driven by ULN 2003 stepper motor driver module, and three 1.5 volt AA alkaline, double A alkaline batteries are used to power the circuit for a total of 4.5 volt. So the implementation of finger ray casting for collision detection is shown here. For each finger, a ray is casted from the fingertip in the forward direction against all object collides in the scene. Then the interaction forces to be rendered are calculated. Three distinct feedbacks are provided. Regarding haptic feedback, the force is rendered by using a pulse width modulation signal where the duty cycle of each vibration actuator is proportional to the force to be rendered normalized between the specific actuator range. Regarding auditory feedback, the rendering is obtained by generating a sound feedback with the pitch that is proportional to the force to a rendered normalized between the specific frequency range. And regarding the visual feedback, visual rendering is achieved for the collision points by generating a color feedback with a wavelength that is proportional to the force to be rendered normalized between the specific wavelength range. So these mathematical equations are related to the calculation of the force, vibration, pitch frequency, and a wavelength regarding the calculation depending upon the distance and the approaching velocity, stiffness. So these are the mathematical models which are basically used for calculation of these uh, feedbacks. So a unified modeling language sequence diagram is shown here depicting the interaction with the virtual object. The most interesting aspect is that haptic, auditory, and visual feedback are rendered in parallel, therefore offering a realistic and immersive interaction experience. So in this order, as it is shown here, UML sequence diagram, the procedure for rendering of tactile feedback is shown. For each finger, the Arduino board serves as a driver to trigger the corresponding motor vibration. So to demonstrate the potential of the proposed framework, a case study is presented in particular. Educational approach to the recycling and disposal of the domestic waste is considered. Uh, the aim the aim is to increase the both academic and public awareness for this purpose. The underlying idea is that the user would learn how to properly sort out home waste by participating into a multimodal auditory visual tactile experience. The goal is to sort all the waste materials in the shortest time possible. So each participant is first asked to familiarize with the simulation environment and successfully is asked to perform the following test sequence: sorting materials by using only visual feedback, then sorting materials by using auditory and visual feedback, and then sorting materials by using combined auditory, visual, and tactile feedback. For each test, a timer is started, and when the user first touch any of the waste object, the timer is stopped when all the waste objects are properly sorted. So the experiment is repeated with 10 human subjects. As you can see, on average, every human subject performs better when all three sensory feedbacks are enabled. So this means that with these sensory feedbacks, with the visual, auditory, and tactile, it is very effective for the students to complete the task in a less time. So, moreover, for the assessment, a user survey is conducted immediately after a test session. In the particular, the group presence questionnaire (IPQ) is considered. The IPQ test is scale for measuring the sense of presence experience in a virtual environment. The current version of the IPQ has three subscales and one additional journal item not belonging to a subscale. So the three subscales which can be regarded as an individual independent factors include spatial presence, the sense of being physically present in the VE, Involvement, measuring the intention devoted to the VE and involvement experienced realism, measuring the subjective experience of realism in VE, and the additional general item assesses the sense of being there and has a high loadings on all three factors with especially strong loading on special presence. So the IPQ survey results for the proposed multimodal rendered experience is shown in the figure. As you can see, the results are promising in terms of realism and spatial presence. Involvement might be improved. So this study basically introduced an involvement of haptic-enabled framework for hands-on e-learning for to offer safe digital access to laboratories. A fully immersive tactile, auditory, and visual experience is achievable thanks to the proposed framework. This is accomplished by merging VR tools with novel wearable haptic devices created by supplementing a low-cost commercial off-the-shelf controller with vibrotactile actuators. So the Unity gaming engine and the Valve Knuckles EV3 controllers are used for this purpose. A human subject research was performed to validate the proposed framework. The considered enabled framework boost student engagement and the perception of the spatial presence, realism, and involvement. So, as in the future work, the proposed framework could be used to develop teaching modules and to test the concept with engineering students in experimental setting. And this would make it possible to evaluate the applicability of the concept as on a longer and practical scale. Thank you so much.